Good morning. I'm Christine Sa. Welcome to this news briefing from the 250th National Meeting and Exposition of the American Chemical Society in Boston. We're joined today by Dr. Stuart Licht from George Washington University. He's going to talk to us about a new approach to removing CO2 from the atmosphere, turning it into carbon nanofibers. Dr. Licht.
Thank you very much. One of the great threats facing our planet is climate change. Rather than attempt to survive the climate change consequences of flooding, wildfires, starvation, economic disruption, human death, and species extinction, we must mitigate the greenhouse gas, carbon dioxide. Sequestration attempts to bind carbon dioxide within other substances by blowing CO2 back into the ocean or bubbling it into the earth or other methods. But sequestration is fraught with uncertainty, high costs, and is unlikely to succeed. We report today that we have found a viable solution to mitigate climate change. Instead of sequestration, atmospheric carbon dioxide is directly transformed into stable, useful, compact, valuable carbon products. In the simple procedure, the carbon dioxide is converted into carbon nanofibers. Carbon nanofibers are a valuable, pure carbon-based substance with strength greater than steel, and useful properties for building, for nanoelectronics, industrial catalysis, and for higher capacity lithium-ion batteries. Until now, the carbon nanofibers have been too costly for most applications. Here they're grown efficiently and at very low cost using solar energy. They're grown in an electrochemical reactor, and the electrochemical reactor is illustrated in our animation, if we could start that. In the animation here, we show electrodes immersed in molten lithium carbonate. Electricity is applied, simple electricity, between the two electrodes. At the lower electrode, the cathode, the lithium carbonate, common substance, is split into carbon and lithium oxide. This carbonate at the upper electrode simply releases pure oxygen. The lithium oxide that was formed at the lower electrode reacts with the atmospheric carbon dioxide to make more lithium carbonate. And by this means, the lithium carbonate is continuously replenished. The simple overall reaction is that carbon dioxide comes in from the air, and carbon is made at one electrode and oxygen at the other electrode. But this carbon is in a very special form. It's in the form of carbon nanofibers. And the chemistry, the specific chemistry, is very straightforward, very simple to make the carbon nanofibers, and it's delineated in our new publication. It's available free online as an open access article. The reference is given in the animation. Also, if you're interested in the specific chemistry, just shoot me an email. My email address is also on that animation, and we'll send you the full 2-minute animation of that process. Carbon nanofibers are a very valuable product, as opposed to coal, which costs about $40 a ton, or graphite, which costs about is worth about $1,000 a ton. Carbon nanofibers are worth on the order of $25,000 a ton. We think this gives a very large impetus to convert the carbon dioxide directly into carbon nanofibers from the atmosphere, and provides a reasonable path to bring down the carbon dioxide levels in the atmosphere. Today, carbon nanofibers are used in carbon composites, such as in the Boeing Dreamliner, the lightweight replacement for the body of the plane instead of aluminum magnesium alloys. There's a variety of applications for them, and we believe that this process will substantially bring down the price of carbon nanofibers, driving up the demand for them. We believe the carbon nanofiber market is just at the beginning, the same situation as the plastics market was at the beginning of World War II. It's about to take off. There'll be a wonderful variety of applications, from building materials to renewable energy uses to nanoelectronics. And with that, we provide a wonderful buffer to store the carbon dioxide that was in the atmosphere into a stable, compact form. We're very excited about this process, and I'm available to answer any questions, please.
Great. Thank you, Dr. Licht. Do we have any questions?
Matt Gunther, Chemistry World. It's really nice, your illustrative example on the screen, but how difficult will it be to scale up this process, or is that even your intention?
We are involved in scaling up. Here is, let me see if our first attempt to scale up. I want to emphasize that we are a fundamental chemistry laboratory. We're not chemical engineers. I don't want to state what we can't do, but it's a very straightforward process and very easy to scale. Our initial experiments were on the order of 1 amp. The 1 amp provides about 0.1 gram of carbon nanofiber per hour. We scaled up more than 100-fold to well over 100 amps. At 100 amps, we make 10 grams per hour. This is part of a sample from our 100 amp run of carbon nanofibers produced. It's in scaling up more than 100-fold, there is no extra loss in energy per unit mass of the material, so it scales up very, very easily. The entire process is quite low energy. So we're excited about that, but I don't want to minimize the amount of resources that will be needed for chemical engineers to correctly scale up and continue with the process.
If you could please state your name and affiliation.
Hi, Josh Sokol, New Scientist. We spoke earlier this week. So the press release mentions a figure of $1,000 being the electricity cost of running the process. I guess that's at 100 amps. But obviously there's also cost. You could offset that with solar power providing the energy for it. There's cost of the lithium. There's cost of the specific, process that goes beyond pure power. So when you cite that figure of $25,000 as the value of the product, what do you think is an accurate figure for the cost of at this level of producing it?
Well, these analyses will go on in more depth in the future, but the system is very comparable to the process used today for solar power towers. The solar power towers exist in Spain, in the Mojave Desert, in Australia, in the outback, and they utilize reflecting mirrors up to a central point. They focus the light on a hot water source. It makes steam, which runs a turbine, and the turbine makes electricity. The costs of that are competitive today. They're using it to make electricity. In our system, we simply would have to replace that steam turbine with our electrochemical generator. That concentrated light that's available there provides two things. It provides the light, the visible portion of it provides the light to make the electrons using concentrated photovoltaics. And in our paper, we show we can do that very efficiently with 39% efficient solar concentrated photovoltaics. The rest of the light that's not used by those solar cells, it's the heat, the infrared, is used to heat the process and provides the heat there. So overall, it looks like it's quite a competitive process. But a specific dollar amount is similar to the cost per watt hour needed to run a solar power tower, for example.
Do we have other questions? Yes.
Ben Fowlsley, Chemistry World. Does that mean that this is actually only an efficient process in places where you get enough sunlight, so places like Spain, Australia and so on, where you can use a solar collector? Or would there be ways to put this in other areas where they don't get as much sun?
We run this regularly under Washington, D.C. Sunlight, and so we have there a heliostat, a series of heliostats that follow the sunlight, and the entire reactor and CBV on the heliostat. And that DC sunlight is more than adequate to maintain the temperature needed for the process.
Thank you.
So with the system that you've developed at GW, you're actively pulling CO2 from the air around Washington, D.C.
Yes, that's what these carbon nanofibers are made from.
We've got Washington, D.C. area. That's great. Yes?
Matt Gunther, Chemistry World. Looking at your electrode setup, you mentioned that a very specific form of carbon is formed on these electrodes, be it nanofibers. Is that because the system was specifically engineered to create these nanofibers, or is that just a natural consequence of the process that is occurring?
No, it's a specific level of understanding of the process. We've been involved in this for quite a while. The carbon nanofibers are a very exciting consequence of that. The carbon nanotubes and carbon nanofibers, a subset of them are graphite layers which have arranged themselves into very small fibers. We purposely add a very small amount of a transition metal. I'm sorry if I'm going a little bit tech here, but including nickel, cobalt, copper, or iron. Specifically, nickel is shown in several times in the paper, but the other ones too. These small concentrations produce little islands of metal, tiny islands of metal on that lower electrode, on that cathode. Those tiny islands give us a wonderful base from which the carbon nanofibers grow. So they grow out from there.
Do we have any other questions?
There's an online question from Sophia Kai, ACS News Service. So cost reduction isn't the primary motivation for this technology, but she asks, how does the cost of creating these carbon dioxide derived carbon nanofibers compare with the cost of making traditional carbon nanofibers?
It's much, much less expensive. The traditional ways, two principal methods of making carbon nanofibers for carbon composites are chemical vapor deposition and pulling and spinning. Pulling and spinning involves a polymer, which is individual strands which are pulled to very thin dimensions and then carbonized to remove all the other materials in the polymer, and then woven together to make strands. It's a very expensive, time-intensive, and instrument-intensive process. Chemical vapor deposition involves evacuating a chamber and layer by layer adding different organometallics to build up these. They're very expensive processes. On the other hand, here we have two very simple electrodes, a steel electrode and a nickel electrode immersed in a liquid. We just add simple electricity and the materials grow. The cost of the electricity is low. I want to emphasize that the electrochemical chamber by itself is sufficient to make the carbon nanofibers. The use of the renewable energy makes the entire system consume CO2. But we can run the electrochemical chamber just by itself. And of course, the cost of electricity is on the order of 10 cents a kilowatt hour today. So it's a very inexpensive process.
Jonathan Webb from the BBC. Just on that comparison is quite striking. You've got these complicated processes with a lot of physical manipulations, and yours just grow. Is the structure of your nanofibers exactly the same as the ones that are being manufactured at the moment?
Yes, but we need different structures for different applications. And so in the paper we show two things, that we can make a profusion of different shapes and sizes, and we show conditions by which we can make very specific, uniform carbon nanofibers also. And I think we're under a bit of a time constraint, but different applications have different characteristics. You want strength for the batteries. You want to have short nanofibers so that the lithium ions can get in. For strong epoxies, you want moderate length carbon nanofibers of certain dimensions, and for a woven cloth, you want longer ones. So it depends on the application. But we've shown that we can make a large variety of them, and also that we can make very uniform straight ones also in that paper.
So it's Kath O'Driscoll from Chemistry and Industry magazine. Just irrespective of making carbon nanofibers, you made a comment in the press release about just 10% of the Sahara Desert to mitigate climate change. How much would that cost?
Well, we've been studying the process of converting CO2 into carbon for a while. The carbon nanofibers are quite new, but in 2010 we published that to convert carbon dioxide into graphite, I presented a series of calculations that showed that less than 10% actually of the area of the Sahara Desert was needed with the concentrators. That sufficient rate of insulation would convert the CO2 over a 10-year period into carbon, such that we can bring carbon dioxide levels down from existing levels down to pre-anthropogenic levels, down to pre-industrial levels. This would require a lot of money. We have a massive problem here. We need a massive global collective working together to build such a site. So I don't want to minimize the effort that's involved, and that we need chemical engineers and dedicated scientists and politicians to bring this about.
And would you envision that there would be multiple systems located throughout the world, or in one location would be enough?
Areas of very high insulation would be particularly good for this, and so that would include multiple installations. I mentioned the Sahara Desert, but also the Mojave Desert in the States, the Outback in Australia would all provide very good locations for this.
Great. Do we have any other questions? All right, I think that's it. Thank you so much, Dr. Licht. The archived version of this session will be posted at bit.ly/ACS Live Boston. Please join us for our next press conference today at 10:30 to hear about new compounds that could one day help treat alcoholism. Thank you.